We got it? This is an all skate. We can all do this one. Again, I'm going to push on the book. It's going to stay right against the wall. I'm going to apply the force at 45 degrees to a 2-kilogram book. But the book's not going to slide, but it's not going to need friction. How much force would I have to apply? You should be able to do this. And by that admission, I'm afraid I have to do this. Now, look, I think we have gravity acting downwards. Seemed like a pretty straightforward way to go. Nice starting spot. 20 newtons. There's an applied force at an angle. It has to be a large enough force at 45 degrees to be able to hold the book in place. So I am attempting to look at this portion to make it drawn so that it's the same size as this portion. Remember, the size of the vectors is becoming more important now. So this is my applied force. Right? I have to draw that one. I have no choice. It was given to me. Then, is it touching any surface? Yes, it's touching the wall. This way. There must be a force this way. Those are my forces. There's no friction. That was not just implied, it was explicitly stated in the problem. That friction is not required to hold the book in place. That's it. So you break this up into components. And I do feel as though I can skip some stuff. For many of you, I can. Some of you, I can't. You're barely holding on. You're going to need to improve because we got big stuff coming soon. F cosine 45, F sine 45. Any question about that? Well, net force in the y direction is F sine 45 minus 20 equals 0. F equals 20 divided by 0.707. That is 28 newtons. That's it. That's not the point of today. That's just to get us started. So the point of today. If I push with 30 newtons, the book's either going to start to slide or friction's going to spring out of nowhere and hold the book in place. Everyone understand what I just said? I push with 30 newtons. I push with more force. Don't change anything else. Just push harder on the book. If the book stays in place, then friction's holding it in place, correct? What direction would friction be? It'd have to be downwards, right? Because if I push, I won't say who pointed up, but I love you people. But if I push harder on the book upwards, friction trying to hold the book in place is going to pull down to prevent it from going up. It prevents one surface from sliding past another. If I apply 25 newtons to the book and the book stays in place, friction acting on the book, very likely what direction? Upward. So I can apply less force or more force, but the book probably stays in place if there's any static friction. You see, static friction is an inequality. It will increase to meet the demands of the problem up to a threshold. So I can start increasing this force, and the book might just stay there for a while until I reach the threshold. Right? The threshold is the maximum amount of frictional force that can be there. That's why this is an inequality. If I push just a little bit, I'll probably just get a little bit of friction. Push a little bit more, I get a little more friction. You understand that the more friction, more I apply a force, the more friction will probably show up to keep the book from moving. That means there's a range of forces that I can apply, and the book will still stay against the wall. You understand what I'm saying? Because that happens in the reverse. If I start lessening the amount of force I'm applying, then there will be an upwards frictional force, and that upwards frictional force will keep getting bigger until I reach the threshold. And then it'll start to slide. I want the range. What's the smallest force and what's the biggest force? Let's say that the coefficient of static friction is 0.3. I would like you guys to tell me the smallest force and the biggest force. Now, some of you Have no trouble. Go, run. Run, my younglings. Do it. Make it happen. Some of you need a place to start, so start by picking one of these to do. And by the way, I've looked at your notes. Your notes are useless. Why don't you write down what it is we're doing? If you want your notes to be useful later, say what we're doing. We are going to adjust this force. We're going to make it bigger and smaller. And we're going to see how big can we make it before the box starts sliding up the wall. And how small can we make it before the box starts sliding down the wall. That's what we're attempting to do. So write that into your notes, so your notes tell you something. Then, once you've written that into your notes, how big and small can we make F before the book starts sliding? I assume it's going to get bigger than 28, smaller than 28. It's going to be in that range. This might require two different free body diagrams. One to handle the case when the force has gotten bigger and the friction's in one direction, and one to handle the case when the force has gotten smaller and the friction's in another direction. Pick one and try it out. This is what we call a threshold problem. We are approaching a threshold. So let's speak about some of this real quick. I want to talk about the maximum first. Let's do that one first. What's the maximum force we can apply before the box starts to slide? One of these has not changed. That's the downward force. Right? It's still going to be 20 newtons. The book's weight is the same. We are pushing upwards and to the left with a larger force than before. So this is going to create a larger normal force as well. So this isn't just a direct proportion or something. So we have more normal force, so that gives us more possibility of friction. But the friction is trying to prevent the book from sliding, in this case sliding up the wall, because this is bigger than the 20. So suddenly there will be a frictional force, and that frictional force will need to be downwards. Now, there are three unknown forces here. We don't know the frictional force, we don't know the normal force, and we don't know the applied force. Even when we put together our coordinate system will help us because we do know at least one of the forces. So if I put my coordinate system in there, put my 45 degrees here, and by the way, so far everything we're doing here is all fair game for your test. I might not ask one with a static friction question like this, but having you work this level of problem out is fair game. F cosine theta there, F sine theta there. None of these choices are much different than before, right? Now, if I apply Newton's laws, I'm still doing the exact same thing that we've been doing for the last 2 weeks. In the x direction, I will have F cosine theta minus normal equals 0. In the y direction, I'll have F sine theta minus friction minus 20 equals 0. Now look, all of you who are struggling, this isn't new, but every time I do this, I go through and I circle, okay, there's this force in this direction, this force in that direction, marking them off, making sure I'm capturing them. And there's 2 in that direction, and there's 1 in that direction. Making sure I'm capturing them all, right? Up and down versus left and right. Some of you are bewildered. But we're breaking it into one-dimensional problems. That's what our goal is. Our math is only one-dimensional. But even when I'm done, I have an equation with force and normal, and another equation with force and friction. That's 3 unknowns. We have one common unknown here. But I only have 2 equations. So with 3 unknowns and 2 equations, that's not enough to solve it. But this is what Newton's laws produce. It produces one equation for each direction of motion. But we have more information now. We have learned something new, that friction can be up to and equal to mu times the normal force. If we're looking for the maximum, then we are looking for the point where we have reached the threshold. Right? The maximum applied force is when I get the maximum frictional force. This gives me 3 equations with 3 unknowns because I gave you the coefficient of friction. It was 0.3. Now you need a method or a thing to do here to get to your answer. And you have some choices. For example, we could put these 2 things together. Right now, we could just put those 2 things together. That would give me one equation that has the applied force and the normal force in it. That's not enough to solve the problem, but I can use this formula and this formula now. That's 2 equations and 2 unknowns to get rid of normal force between them. All of this is just algebra. And algebra that you're supposed to be, relatively proficient at. Solve that for normal force. And largely done, right? All that's left now is a little bit of arithmetic. Maybe factor out the F. We all see it here? It's okay? So this gives us like 40 newtons. The only difference when we look for the minimum force is that this is going to be drawn up there. It's the only difference. Because we're going to make this force smaller. That'll make this force smaller. But the box is going to slide down. That's only one change to all of this. One place where that makes a difference. Right here. It changes that from a negative sign to a plus sign. It's the only change. I mean, you guys who are inexperienced probably should start the whole problem over and draw, a new free body diagram, because I'd hate for you to miss out on that opportunity again. Because, we haven't done this enough. Maybe something that looks like that. I've made the force smaller, but the weight's still 20 newtons, so the normal force is now smaller. It's not balanced up and down, so I'm going to need some frictional force upwards to balance the weight downwards. All right, this is our new free body diagram with this force made smaller in proportion to the others. So the frictional force has to be upwards. Everything else works out the same. I leave this to you as an exercise. You need the practice. I don't. The thing about this is that's an inequality. I want to show you something else, a different way to approach this problem. All right? For the time being, I'm going to assume we're dealing with the same problem. So this is F cosine theta, and this is f sine theta. I'm purposefully going to leave everything in terms of their original variables. Not to make it look more complicated, but to show you something else you can do. The net force in the x direction still equal to 0. That's f cosine theta minus normal force equals 0. In the y direction, we still have the same kind of stuff, right? We have f sine theta plus friction equals mg. Minus mg equals 0. Something you can do is, instead of waiting to reach the threshold, you can solve both of these for friction and normal force. I would encourage you to consider doing this. Take this and sub it in for the normal force. Take this and sub it in for the frictional force. Leave the inequality intact. This is called preserving the inequality, giving you an inequality for an answer. Because when you do this, mg minus f sine theta less than or equal to mu times f cosine theta. You now have an expression that has an inequality in it. You can figure out what happens or where the value is on what side of the inequality. You'll be asked in AP questions quite a lot, do you have to stay above a certain value or below a certain value? Leaving the inequality gives you a chance to answer that question.